co-host, so you should be able to unmute yourself and start sharing your screen. This
Hey,
is
how you doing?
next speaker. Hi, Ali. So since we are on over time, let's quickly get into the second talk. It is my absolute pleasure to introduce to you Ali Donaldson, a professor in the Department of Computing of Imperial College London, as well as a senior software engineer at Google. At Imperial, Ali leads the multi-core programming research group, where he worked on the GraphicsFuzz project, which spun into a company. We became GraphicsFuzz Limited, which was then acquired by Google in 2018. And at Google, Ali continues his great work of automated graphics driver testing. Thank you, Ali, and please take it away.
Thank you very much, Azalea, and thanks, Rupak, for the excellent talk. Really enjoyed that. It's a real pleasure to give this talk at PLMW. As Azalea said, for the last couple of years, I've been both an academic at Imperial College London and a software engineer at Google. And the reason I joined Google is because my startup company, GraphicsFuzz, which was built on some research I did at Imperial College London, was acquired. And since then, I've been thinking quite a bit about some of the similarities and differences between entrepreneurs and researchers. And I thought I would give a talk based on some of my thoughts about those similarities and differences. So I'm basically an academic with some forays into entrepreneurship in industry. Straight after my PhD from Glasgow, I was a developer at CodePlay, which is a compiler company in Edinburgh that was very much in startup mode at that time. And then I went back for a postdoc at the University of Oxford and have been an academic at Imperial for about a decade. And in 2018, I founded this company, GraphicsFuzz, which was acquired by Google. And I've been at Google since summer 2018. I'm actually going to return full-time to Imperial in a few weeks' time. So from mid-February 2021, I will be back full-time as a professor at Imperial. But who knows what the future will bring in terms of other forays into industry. So I'm going to focus here on the common ground and also the fundamental differences between researchers and entrepreneurs. And I'm going to draw an analogy between the lean startup movement, which is very popular in the startup world these days, and what we do in research, and think about whether there might be a kind of lean researcher we might want to model ourselves on to use some of the good things from entrepreneurship and entrepreneurial skills in our research careers. So I don't know how interactive it's possible to be here. I wanted to come out of my present mode and get some thoughts from you all about what researchers and entrepreneurs do. Azalea, how feasible is that? Can people just unmute themselves and shout out, or is that going to be a bit cumbersome with the
It is not possible for them to unmute themselves, just to avoid, but they can raise their hands and I'll immediately unmute them if they want.
Okay, yeah. So does anyone want to maybe say a few things about what researchers and entrepreneurs do that might be very different or might be somewhat similar? If you have an idea, raise your hand. Azalea will unmute you and we can try and get a few ideas down here.
I don't see any raised hands.
I have some thoughts of my own coming up, but let's give it a few more seconds. I'll have a sip of water in the meantime.
Okay, Santiago.
So I can give it a try?
Yep.
Go for it.
And then Gabriel. First, Santiago.
Sorry. I think one thing common might be problem solving, because, well, researchers are only trying to solve theoretical problems, and entrepreneurs are trying to, well, to develop a product or service, so they will have also problems that come up that they will need to resolve.
Yep, that's a really good example. So, yep, definitely problem solving.
There is also Guillermo, if you want to.
I suggest get funding.
Right. One of the best things about academics is writing grant proposals. We all love that. Absolutely not. Yes, so grant proposals.
There's also Cesar.
Yeah, I would say they have to sell their ideas to convince others their ideas are good.
Yep.
Gabrielle or Stefan, one of you.
So I would say they want to please their customers, but the customers are different.
Yeah.
Michael.
Well, I can't really speak for researchers, but entrepreneurs, it's often fail hard and try and do it with somebody else's money.
Right. So that maybe is a good example of something that is not necessarily what we have in common, except someone else's money might be the money of a funding body or a government agency. Yeah. Cool. Anyone got any ideas about things that they don't have in common, like fundamental differences?
Entrepreneurs make money.
Entrepreneurs make money. Okay. Yeah. Well, I was going to say they might make money.
So I have some common, like they're both trying to do something new, or like unexplored ground.
Is that necessarily true? I'll say disputed.
Maybe not always. I guess many. Yeah.
Yeah, I mean, I would say I'll come back to that point later in the presentation. So maybe rather than saying what I was going to say now, I'll just say it later on. So yeah, I think that to some extent they're both trying to try something new. I guess there's a kind of fundamental difference between how much novelty matters, respectively. All right, thank you so much for that. It's nice to have some interaction. I think it's one of the things that's hardest in these virtual events. So thanks very much for that. All right, yeah, the common ground I had in mind were I think some of those were covered by the answers we had here. One thing that I think is super important in research that also is important when you're doing entrepreneurial stuff is finding an important niche. So if you want to be successful as a researcher, we all would like to do big, grand things, but realistically speaking, it's kind of important to find somewhere where you can slot in and you can at least do some small, modest things that maybe can blossom into big, grand things, but you've kind of got home where you can do something that is not kind of already being done by other people. And I think as an entrepreneur, you clearly need to be able to have some idea, some product, some service that is maybe not too dissimilar to other things that are going on in the world, but it's not too similar that it's already being done and that you don't have a way of making a business from it. I think something that is challenging about being a researcher and also about being an entrepreneur is tailoring what you do to your audience. So if you think about some work that might be more theoretical, it might be that in programming languages, say, it might be that at certain conferences like LIX maybe, which is a logic conference, you may be able to just make this work be unashamedly theoretical, right? You can just present it for its pure kind of glory as a theoretical idea. At a more practical venue, you might need to do a really good experimental evaluation of some sort, even though that's maybe not what you're passionate about. I think when you're an entrepreneur, you might be pitching to an investor, you might be pitching to a company who are potentially going to acquire you. You may just be trying to sell your product to customers, and being able to tailor what you do to specific audiences as a really important skill. Pitching, every time you write a research paper, you're essentially pitching your idea to the folks who are going to review that paper. When you give a talk at the conference, you should be pitching so that people who have seen your talk are desperate to go away and read your paper. And when you write a funding proposal, you're pitching to the reviewers of that proposal and maybe the panel who will then decide which proposals to fund that your idea is worthy of funding. And that's very similar to the way entrepreneurs have to pitch their ideas to investors, companies who might want to acquire them, etc. So, a little typo here, develop a brand, that should say. So something that maybe is less essential in research, but I think is worth thinking about, is developing your own brand. So if you want to, sometimes I've seen faculty candidates' CVs get criticized by being a bit all over the place. They're doing this, they're doing that, but there's not necessarily a kind of common theme through their work and a particular vision that they present. And I think sometimes with your work, it can be great to do things here, there, and everywhere, but it could be worth trying to think about stories you can tell that tie your research together, at least so you can present it when you're going for, a job interview to a hiring committee. And when you're running a startup company, you definitely want to have a clear brand that you're doing. A couple more here: reuse, network, persevere. I will go through them all. So what's this lean researcher idea all about? Well, there's a book called The Lean Startup by Eric Ries that was published some time ago that's been phenomenally successful and has led to this lean startup movement where there are various rules of thumb in the book, guidelines about how to run a startup company effectively trying to make sure that you maximize the opportunities that you get from investment, from a particular experience trying to sell a product, and try and avoid some major pitfalls that many startups fall by the wayside due to. And the kind of key thing from this book, if I had to summarize it in a nutshell, would be try and treat your startup like a lab where you're conducting very quick experiments, where you build a simple prototype of your product, you measure that product to see whether it has market potential, whether it has an audience, and either way, whether or not your product prototype is successful or not, you learn from the experience. You either learn that you're going in the right direction and you go further in that direction, or you learn that actually there were some misconceptions in your business strategy, some misconceptions in your design, and you either go back to the drawing board and think of a completely different business idea, or you tweak your current business idea to account for those misconceptions. So this build, measure, learn cycle is what this book advocates. And you might argue, actually, this is what we do all the time in science. So maybe this lean startup movement is a science-inspired movement for bringing some scientific principles to startups. But I think actually with our research, we don't necessarily approach our research, even though we're doing science, we maybe don't approach the way we do the science in a scientific manner, if that makes sense. So you can do some good science in a very roundabout, non-scientific way that ends up leading to truly good science, but you might pick which research problems to work on and pivot them in a kind of scientific fashion. And I think that some of the ideas from the lean startup movement can be helpful to think about with that in mind. So if I was to simplify the ideas of this book down into kind of 3 core concepts, one is the notion of a minimum viable product, or MVP. This is becoming a bit of a cliche, this term MVP. People use it an awful lot, but I think it's a useful concept. Then a build, measure, learn loop, as I discussed in the previous slide, and deciding when to pivot. So when to decide to work on something different, take a radically different direction, versus persevere, keep going in the direction that you've committed to in advance. So I wanted to go through these 3 things: minimum viable product, build, measure, learn, and pivot or persevere, and give some examples of how I think these relate to doing academic research, research in programming languages in particular, which I'll illustrate through some examples from my own career. But really, more generally, I think these can be applied to computer science research as a whole, if not research in other fields. So minimum viable product. When you're doing a startup company, the idea of a minimum viable product is to spend the least amount of money, the least effort, making something that will give you an indication as to whether your business idea has any merit. So it allows you to fail fast without completely crashing and burning. And it allows you to learn quickly from mistakes and misconceptions about the idea that you had. So in research, I would really encourage you, if you're a new researcher or any researcher really, to always be thinking when you have a research idea, what is the simplest, quickest thing you could do to get some information on whether your research idea has merit? So for example, say that you have a conjecture that you'd like to prove, then it can often be a really good idea to think, okay, is there a simpler version of that conjecture that I could prove? Because if I can't, then it may well be that I am not going to be able to prove the more abstract conjecture, the more general conjecture. Or certainly if I could disprove the more specific conjecture, then the more general conjecture wouldn't hold. If you're thinking about building a compiler from some language into another language that is going to do some cool new optimization, certainly before you build that compiler, you should manually write down some examples in your source language and step through what your optimization process would do on that example, and then maybe hand code the generated code from the target language and check that it really does give you some kind of speed up, right? This will save you. This might be a very painful thing to do. You couldn't do it for tens or hundreds of examples, but it will save you a lot of pain if it turns out that the idea just doesn't have merit. And you'll probably learn a lot of tricks or nuances that will help you when you come to build a tool to automate this process. So whenever you're approaching a research problem, I would encourage you to think really hard about what would be a minimum viable product you could build to assess whether your idea to solve the problem has some merit. And at this stage of building an MVP during your research, quick and dirty hacks are completely fine. They may not be fine in the long run. They may be, you may build some script, or you may do some kind of theory with holes in it that later you want to throw away completely, or you want to massively improve. But at the very beginning, when you're just thinking, how do I get to the nub of this solution and see whether it has any merit, then doing some quick and dirty hacks is absolutely the right thing to be doing. I think my PhD students and postdocs probably get fed up of me saying, come on, just to see whether this has merit, is there a simpler thing you could do? Could you write a horrible script to try this idea out, and later come back and build it more elegantly, write tests, have a lovely build system, or theory analogues of those things? Yeah, and I think it's really good to be very pragmatic at the beginning and have a minimal viable product for your research. Just to make this concrete, let me tell you about a tool that I led the design of some years ago, a programming languages tool called GPU Verify. What GPU Verify is a verification tool that takes a program designed to run on a GPU. The program would be written in CUDA or OpenCL, which are two GPU programming models. And it would check whether the concurrent threads that are going to run that program are well synchronized or not. So if the threads are well synchronized, GPU Verify may be able to prove that and give you a tick and say, yep, this kernel is good. There will be no data races when you run this GPU kernel. Or it may find a possible synchronization bug. So it will give you an alarm of a potential data race between two threads that are going to run the GPU kernel, the GPU program, and say that these threads could race. And it's a sound static analyzer, so it has false alarms. The goal here is to help GPU programmers eliminate synchronization bugs early in the design of their software. And the main challenge of the project was that GPU programs have thousands of threads. So if you would read our papers on GPU Verify, you'll see that there are a whole load of components in the solution we came up with. In particular, we have a Clang-based front end that takes a GPU program and translates it into a two-threaded program and uses kind of smart abstraction to make it be so that just verifying this two-threaded program suffices to decide whether the thousands of threads in the original program are free from data races. So there's a kind of clever translation from CUDA into an intermediate verification language called Boogie. And that translation allows verifying these programs run by thousands of threads to be simplified to the task of verifying a program run by just two threads. And if you would read the paper, you'd see all these components working together. But actually, the minimum viable product for GPU Verify was much more embarrassing than this. In the minimum viable product, I was the compiler that would do this translation of a GPU program into a two-threaded program. So I would go through example after example, and I would manually work out what I would like it to look like in its two-threaded form. And then I would actually implement the reasoning engine on top of Boogie that used the Z3 theorem prover and work out whether it was going to be feasible to verify these two-threaded programs and work out whether any special care would be needed in the translation process to go from the parallel program into the two-threaded program. And every program I manually translated led to something changing in the abstraction that this two-threaded translation was based on. So all the kind of theory behind this was up in the air. The implementation didn't exist at the front end level. It was me translating these programs, and the reasoning engine we were building was changing all the time. And this was actually, once this stabilized and we had pushed through sort of 20 or so examples, we felt confident to go ahead and write a paper saying, we have not got a front end. We manually translate these examples into this Boogie language, and then we can verify them. But here's how we do it. And we'd come up with a kind of stable solution by now. And that was enough for us to write a paper, submit the paper to PLDI, and get it rejected, right? But get it rejected with really useful feedback from the reviewers on how we could improve our evaluation, how we can improve the technique, and a very strong signal that they weren't very happy with me being the front end. They definitely wanted this to be more automated. Another example of a minimum viable product is GraphicsFuzz, which is the technique that I did a startup company on that led to me joining Google. So this is a compiler testing approach. It works by taking a graphics program, a shader, and producing from it a whole family of equivalent shaders by making semantics preserving program transformations. And then pushing both the original shader and all of these variant shaders through the graphics pipeline. And because these transformations are semantics preserving, all of the resulting shaders, when they run on the GPU hardware, should give the same image. So if we get this pretty image of a whole load of squares from the original shader, we should get exactly that image from all of these variant shaders. And if we don't, if we get a difference in the image or a crash, then that's a bug in the shader compiler that we can investigate. So this is a kind of pictorial overview of how the GraphicsFuzz approach works. If you know anything about graphics programming, you'll know that graphics APIs like OpenGL and Vulkan are really complicated. They have hundreds and hundreds of API functions. And the shading languages that you use to program them are also very complicated. So building a compiler fuzzer that would work well in the full glory of, say, OpenGL would be really a lot of work. What we found was there's this website called GLSL Sandbox, where enthusiasts post really nice examples of graphics shaders. Can you just confirm, Azalea, that you can see this Chrome view now instead of my PowerPoint
yes,
slides?
definitely. Yeah.
Good. I'm never quite sure what happens when you could change windows in Zoom. So this is a nice example of a kind of graphical effect that someone has programmed. When I move my mouse, this strange shape explodes apart and then comes back together. And you can see that there's a whole load of C-like code here. And this is not kind of realistic graphic shaders that would be used in games and media-rich applications, but they're interesting shaders that are human-written. And what we decided quite early on in our project was that actually we could use hundreds of these examples from this website as a set of benchmarks if we were to write a paper about our approach. So if our approach would work, these could serve as benchmarks. And therefore, there was no reason in the short term for us to cover any more of the OpenGL shading language than was used by these benchmarks. And furthermore, we first of all chose like some of the most simple ones of those benchmarks and made our tool be able to operate on them, do its fuzzing thing on those really simple examples. Anything more complicated, we said, okay, we'll shelve that and leave it for later. We'll work on these really simple ideas. So the minimum viable product for GraphicsFuzz was hard-coded for those examples. And I remember commuting back from London on the train and trying some of these examples, and suddenly my laptop just started going haywire. I wish I'd taken a video, not just a photo, but you can hopefully see here a bit of the Windows 10 user interface, but with kind of horrible streaks through it. And yeah, my laptop was kind of flashing and going crazy because of a miscompiled graphics shader making the driver go into a bad state. And this was, I remember, the time when I had the idea that maybe we could do something commercial here. We seem to be able to find bugs that really matter, that are potentially security relevant. And all we'd done was written like, I don't know, a few thousand lines of Java code to do some fuzzing on some basic OpenGL shaders. Hadn't even learned that much about OpenGL in order to do this. We just learned enough that we could get something up and running and working to impressive effect, by no means covering the whole space of the language. Okay, so that's minimum viable product. Next up is build, measure, learn. So the basic message here is try to, iterate using your minimum viable product. So you've, in business, you've built some product. You want to then do an experiment with customers to see how well this is going to work and try to avoid investing more money and time in that product if actually there are fundamental problems with it that you could not have guessed in advance. This is pervasive in academia, I would say, but we don't necessarily think about it as build, measure, learn. So as academics, we have at our disposal the possibility to get peer feedback in many ways. You may, if you're a PhD student, be able to get peer feedback from your advisor, who you should regard as a peer, not just as someone who's supervising you. You can get peer feedback from colleagues by having them read drafts of your work and give you feedback. And whenever you submit a paper for review, that's like sending what you've built to be measured so that you can learn from it. I think it's really important to have this mindset, not that you're trying to produce something perfect and slam dunk, get it accepted for publication first time, but rather you're continuously working on a write-up of your research ideas, and that you should be constantly getting feedback from people on how you could improve either the ideas or the way you've described them to the world. So I think that just like in a startup company, getting frequent, regular feedback on your prototypes so that you can evolve your business idea in an information, a data-guided fashion, I think aiming to get early and frequent feedback on your research write-ups is a really good strategy to avoid really going down a long rabbit warren, like developing some theory or developing some tools, only to find much later on that actually there's related work you hadn't come across that someone could have put you onto much sooner, or to realize that you've described it in a terribly confusing way that's going to be fixable by actually kind of going back to the drawing board and formulating your solution in an aesthetically completely different manner. I think it's also a good strategy for building programming language tools incrementally. And I'm going to give you a couple more examples from these two projects, GPU Verify and GraphicsFuzz. So with GPU Verify, we had that minimum viable product I mentioned, where essentially I and a couple of my PhD students were the front end. We would repeatedly hand translate examples into this boogie verification language. And that let us iteratively improve the reasoning engine behind GPU Verify. And then in phase 2, we built a Clang-based front end that would actually take OpenCL and CUDA programs for real and translate them into the intermediate verification language. But we didn't build that front end in a one-shot fashion. We made the front end, first of all, work well enough that it could handle the examples we'd been manually translating, so that we could truthfully then say we had a front end for those examples. And then we would pick an example, and if it had a feature we didn't yet handle, we would think, okay, is it worth us handling this feature? Are there enough other programs that use this feature that by adding front-end support to this feature, we're going to get dividends in terms of having tens more examples, not just another example that we can push through our tool. So we prioritized improving this front end, thinking about the payoff we were going to get, and each time then improving our reasoning engine and making the tool more fully fledged. In GraphicsFuzz, the minimum viable product was desktop only. And like I said, it was limited to shaders that came from that website, GLSL Sandbox. And it only supported the shading language features that we needed to handle the particular examples we'd chosen from that website to push through our tool. Then we started finding bug reports to companies like Intel and NVIDIA. And some of those reports were confirmed as genuine bugs in the drivers that we were testing in their shader compiler. So that was great. It showed us that there was merit to our approach. People were responding to these bugs and confirming some of them as true positives. But some bug reports clarified things that we'd misunderstood about the OpenGL shading language. There were some things related to floating point roundoff that we had not properly understood. There were some things to do with undefined behavior that we hadn't understood. And getting those things clarified early on, before we'd gone to the effort of making the tool more advanced, let us fix them in the theory underpinning GraphicsFuzz and in the implementation of the tool early on. And then we went on to build versions of the tool that would run on Android and iOS and would target WebGL. And this led us to a really big evaluation that let us get a top publication on the work, and then let us have a product that we can go and take to market. Okay, and then the final thing from the lean startup ideas I wanted to dwell on was pivot versus persevere. And here I don't think there's such a good analog between industry startups and academia, because I think there's a lot more emphasis on persevering when we do research, right? We don't want to be constantly changing our mind about the solution to a research problem or which research problem we're going to address. But nevertheless, I think it can sometimes be the right thing to do, to be brave and say, do you know what? I'm fed up working in this field. I know I could publish a bunch more papers in the field, but this is not what I think is the best way I can advance science, or it's not what I want to do with my life. I want to pivot to another area. Or harder still, to say, I worked really hard on this and actually I'm just not getting good results. I think maybe I need to completely retarget it or abandon it and work on something else instead. And I think that that's the thing I hate the most about being a PhD advisor, actually, is agonizing over whether I should sometimes give my PhD students the advice of, do you know what, shall we just work on something completely different and forget what you did for the last year and a half? That never feels like the right thing to do, but it somehow can be worse to get further on and have to make that decision later. I'll give you one example of a big pivot that I took in some of my research. I did a collaboration with my colleague Christian Kadar and our joint PhD student Dan Liu on adding floating point support to the CLE analysis tool. And what we found, we ended up publishing this paper, Floating Point Symbolic Execution, a case study in N-version programming. And you can see it's got, rather than 3 authors, it's got 6 authors. And that's because shortly after we started to work on this project, but not too shortly after our student Dan had done a lot of implementation work, we discovered that there was another research group at RWTH Aachen University who had undertaken a very similar extension of CLI to provide floating point support. We discovered this through the CLI mailing list, and we got in touch with each other. So that group and the Imperial group had at the time, I think, a Skype meeting, if you remember Skype, and we were hoping we could find some kind of key differences on our approach. You know, oh, you've approached the problem that way, we've approached it this way. That's fine. We can each kind of have a niche to actually show some novelty in our work. But it turned out really that wasn't the case. We'd taken extremely similar approaches to extending CLI in this floating point way. So we decided to do a kind of joint pivot where instead of pushing forward and trying to claim to be the first to have done this extension to CLI, we decided to do a different thing and collaborate on an experience report in N version programming for N = 2, where we would not reveal any more details to each other about this extension of CLI that we'd independently built, and continue to develop the extensions of CLI, but with a kind of common specification of how far we wanted to get, and then rigorously compare and contrast the decisions that we'd taken in the two different tools to see what interesting things had come up. Like, were there some particular nasty things in floating point to do with nans and infinities that we'd handled in interestingly different ways, or have we by and large taken a kind of similar obvious solution? Were there bugs in one of the tools and not on the other tool? Were there more efficient solutions to floating point symbolic execution in one of the tools versus the other? And this ended up being not at all the project we set out to do, but I think quite an interesting experience report that was well received by the software engineering community. Another pivot was, which is more of a kind of where do I want to take my research, is how I got from GraphicsFuzz. Sorry, how did I get from, I should say GPU verify. Let me go fix that slide. So how did we get from GPU verify to GraphicsFuzz? And this was via another tool called CLSmith. So GPU verify is, as I said before, a way of doing static analysis of a GPU program. And it can say, you know, this program is good, it's free from data races. But what if there's then a bug in the compiler that compiles that program into machine code? That would undermine the guarantee that GPU verify gives. So this gave rise to the idea of doing validation of the compilers that sit beneath the source language that compile a GPU program into assembly code. So having worked on this GPU verify tool for some years, which was an exercise in perseverance, I pivoted and then worked with some students on a tool called CLSmith for randomized testing of OpenCL compilers. And that was kind of successful, but there are some challenges in real graphics that are not present in OpenCL, which is kind of using GPUs for general purpose computation. So we did another pivot to work on the GraphicsFuzz project. And I feel like now, having, you know, worked on GraphicsFuzz for a while, taken it to industry, shown it can be useful there, I feel now I've done a lot of persevering. I'm ready for another pivot. So looking out for a new problem to work on, even though there's a ton more stuff I could do on fuzzing graphics compilers. I think, you know, having done that for a while, I'm now ready to move on and see what new horizons there are for me to work on. Okay, let me conclude with some thoughts about some fundamental differences between entrepreneurs and researchers, and then I'd love to have questions from you. So I think something that also came up in Rupak's talk was long-term thinking, right? Science moves slowly. There are these numbers that were known about for a very long time before people could rigorously define them or show they had certain properties. And I think that directing our research too much with a startup mindset could be dangerous because it could lead to short-termism. Like, okay, I have this little research idea. I want to show that it's successful and write a paper about it. What do I need to do? That's not really a good way to actually approach science in the long run. So I think if you have committed to a research idea and you do want to write a paper about it because that's a really good way to get it out to the world, then I think using some of the lean startup ideas to work out, you know, what's the depth first thing you could do to investigate your idea and how could you get feedback on it. I think that makes sense, but I don't think we should always be thinking about minimum viable products to get us to the next paper the whole time. I think that would be really bad. Something wonderful about being an academic that I think you just don't really have in industry unless you're maybe lucky enough to work at one of the classic research labs that are far and few between is being able to do curiosity-driven research. So I think if you've got something that you're fascinated by, and if you can find some other people in the world who are also fascinated by it, and will be willing to vouch for your work, then academia gives you a license to go away and work on that. There just needs to be, a small community of people who care enough about it for you to have the permission to essentially go away and work on that. I think that's wonderful, and there's not really an industry analog of that, unsurprisingly. Novelty came up when we did the interactive part of the talk before. So I would say, as academics, our work needs to be somewhat novel, almost to be worth doing at all, right? We don't really want to just be retreading old ground. As an entrepreneur, your ideas only need to be novel if you won't make money if they're not novel. So if you have an idea for a product that isn't terribly novel, but for whatever reason, no one's doing it anymore, maybe, people did this a while ago, but there's no one doing it now, and you can refill a niche, that's completely fine. As an academic, that may not quite be the case, actually, right? The fact that someone published something a long time ago doesn't give you the right to just do it again and claim it again as your own. So I think novelty is more important in academia, or more importance is placed on it in academia than in the world of tech startups. And then rigor, I think, is something really fantastic that's valued in academia. So when you do a startup company, you just kind of want to build something that's good enough to get, say, investment funding or be acquired. And then when you're running a production, when you're running things in production, in some sense, you only need things to be as rigorous as the business demands. You can do some kind of experiments to see how well a new strategy is working. And if the signal seems to be strong, you can commit to it. You don't need to actually rigorously defend it. And I think the fact that in programming languages and in computer science in general, we're encouraged to do really rigorous theoretical work or very rigorous experimental work is wonderful. And that's not something you necessarily get to do in industry or when you're doing startup companies that I think we should treasure. Okay, so those are my thoughts about some of the relationships between academic research and industry and startups. I hope you've enjoyed the lean researcher analogy, and I'd be delighted to take any questions. Thanks.
Thank you so much, Ali, for a wonderful talk. The analogy was lovely. And I must also say, on a personal note, I'm delighted that you're coming back to Imperial full time. I think this is the first time I heard this news, so that was great.
I'm looking forward to it as well.
In the meantime, if you have any questions for Ali, please either raise your hand here or post it on Clouder, and we will read out your questions from Clouder. So there's a lot of thank yous on Clouder for an insightful talk. Right now, my Clouder has crashed, so I'm refreshing it. So if any of the other co-hosts can see any questions there, please read them out. Oh, Clouder.
I don't see any more questions right now. But I thought I would ask maybe a quick question, given that we're kind of back on time. First of all, Ali, for the talk, really insightful and really interesting. I think a lot of the points you made are definitely very good ideas, but I think, as always, it can be difficult to judge maybe things that are a bit on the margin, right? So things like if you want to pivot, at what point do you kind of make this decision? And I think everyone has their own kind of perspective on, when do you decide that you want to change something up or go in a new direction? Can you say a little bit about, how you kind of approach this problem? I mean, there's no perfect solution, but I'm wondering your take on it.
Yeah, I don't think I've got any good advice regarding the pivoting versus persevering problem. I think that is the hardest one, and I don't think I'm particularly good at it, frankly. So I sometimes berate myself for working on something for too long and feeling like I'm coloring in the details rather than kind of defining the map of the area. And sometimes I feel like I'm working on too many disparate things and changing my mind the whole time. One thing I would say, though, is that about the MVP, I do find it hard to convince people in my research group to simplify, and take this deep slice, showing like by hook or by crook that their idea has merit, because if they can't do it by hook or by crook, then it probably doesn't have merit. And I don't really ever think that's a bad idea. I think trying to sort of show that you could get a simplified version of your idea working end to end always has to be the best place to start. That's how I build software. That's how I think about theoretical stuff. That's, I think, how you would kind of formulate a business plan. But I do find it can be hard to actually get people to take that advice. So I don't think there's anything nuanced about the advice, but I think sometimes people, I think maybe it takes confidence to even like simplifying things down and saying, can I even get this thing to work? I think sometimes it can be demotivating. You can think, well, who cares if the answer is yes? If I can push this one example through my framework, no one's going to be pleased about that. So why don't I try and do something harder straight away that people will be pleased about? But actually getting that one example through just to show to yourself or your advisor or your collaborators that your idea has merit is, I think, so important.
I agree. Thanks a lot.
So before we stop for the coffee break, are there any other questions for Ali? I personally have some technical questions. Oh, there is a hand from Travis. I'm going to unmute you. Just speak up. Yeah.
Yeah. So I thank you for the talk. Actually, I really enjoyed it. I have a couple questions, I suppose. My experience, I guess, with Lean, like in an industry environment, not Lean specifically, but like fast iteration with smaller teams, is that they tend to run better democratically, or at least with everyone who's a stakeholder having that voice. Has that like impacted the way that you organize your lab, or has it changed the way that you you work with your team members or your advisees, I suppose, more as team members?
Yeah, I guess that I haven't too much had a chance to try this out in earnest, because when I went nearly full-time to Google a few years ago, I deliberately tried to let my academic pipeline drain a bit, because at first it was very hard to keep on top of, my 100% commitments that don't just go away when you go down to part-time. So when I had a bigger research group a few years before I joined Google, I wasn't really thinking in this mindset. So I don't think I was trying to kind of run things in that way. So yeah, I don't have too much experience of it now, but I would say that, yeah, I think this would not work that well if you had a kind of research group where there was a lot of orders being kind of placed from above to other people in the group. I think it does involve a kind of collegiate atmosphere. I also think that's the right way to run a research group anyway.
Okay, thank you very much. Appreciate it.
You're welcome. Thank you.
There's also Michael.
Yep. Oh, can you hear me?
Yes. Can you hear you? Hi, Michael.
Hi. Yeah, it was for me, this was a really interesting kind of analogy to hear, because, well, coming out of a whole bunch of years in industry and being around a lot of entrepreneurs,
yeah,
it's kind of fascinating because, well, especially when you got to the pivot persevere thing, because I've been through sort of multiple generations of watching entrepreneurs pivot far too early, simply because of their sort of profit demands of the business that they're in. Like they've gotten the product to a certain point, and then the cash is going this way. So it's easier to pivot than it is to persevere. And I think that's often led to, like, part of my reason for being interested in going into research is because I feel like that's often led to us kind of truncating lines of inquiry way too early, and actually in the long run, I think we've abandoned a lot of products that would have been really of use. So I guess I'm just kind of wondering, like how would you apply this? I'm just coming into research. I'm sort of transitioning out of industry, so I'm trying to figure out how would you apply the idea to sort of keeping on that. How would you apply the idea of the lean approach and the minimum viable product, which we come in out of industry with, like, minimum viable idea and what gets us to profitability, in a world in which you're sort of, in which persevere is probably the better idea, in a certain sense, to progress the front end.
That makes sense. So I think the pivot and persevere is probably the place where the analogy is the weakest, because actually I think in research we all know that, like, there are people who've worked on problems for a very long time and finally someone's cracked it. So if everyone was pivoting, people wouldn't kind of crack those problems. I would say probably for me, I more think about when strategically in your career should you think, do I want, like, to consciously think, okay, I could be the person who does whatever it is you do for the rest of my career or for the next 5 years, and that might be fine, but do I want to do that? And if
Yeah.
so, I should do it because I want to, or I should maybe pivot and be brave and think, okay, I am going to like take the foot off the gas in terms of the output from my research group, maybe have fewer PhD students because PhD students need to publish to graduate or to get a job. So if you actually want to go into a new area, you might need to say, you know what, I'm not going to apply for funding for a while and I'm not going to take on any students because I want to go and do some reading and I don't want to start like exploring too much with other people who may fall by the wayside of my bad decisions until I've found my feet again. So those kinds of pivots, which I guess are quite different to the kind of industry pivots. Another thing though is I think that if you built a capability, a research capability, like say you have some static analysis tool, or maybe you haven't, say you've built some optimizing compiler, you may never have thought about the fact that the preconditions for the optimizations are themselves a static analysis, and there may be a bunch of problems in software reliability to which you could apply those analyses. So sometimes I think it can be a bit of taking a step back and seeing your idea as a hammer and looking for other nails, right? Sometimes people are doing too much of they have a hammer and they find nails, but sometimes people are so focused on I do this kind of research, they may not think, well, you know what, actually, I don't have to do that kind of research. There are aspects of what I'm doing currently that I could apply elsewhere. So you could like, you know, spread out a bit and not necessarily pivot completely to those areas, but do some side projects, some collaborations using, you know, those ideas that are more generally applicable.
Right. Okay, thank you.
Thank you so much, Ali. Let's thank Ali again. And I'm going to stop the recording now. We will upload this later on to YouTube for anyone who missed the talk. But thanks again, Ali. We have the coffee break now. We'll be back here in 20 minutes for the next session. Thank you, guys.